Okay, welcome back. This is lesson 4, and what we're going to do now is change our focus away from energy changes that happen with physical processes to energy changes that happen in chemical reactions. Remember what I said at the very beginning about potential energy. You may have to go back and review this concept, but we said that with chemical reactions, you can have differences in potential energy based on the differences in composition. And what this means is that the the bonds that you have between atoms in the reactants can be different in potential energy compared to the potential energy of the bonds in the products. And this is going to result during the chemical reaction of either energy being absorbed or energy being released during that reaction. So now this is what we want to investigate. And the principles that we learn for the physical processes are in fact the same for the chemical reactions. So let's dive right in. The first reaction that I want to look at is one that you guys are actually familiar with, which involves taking sodium hydroxide, which is normally a white crystalline solid, dissolving it into water. Remember Pete's rule that when an ionic compound dissolves, it has to be ionized. So you add the NaOH to water, and what's going to happen is it's going to dissolve and it's going to produce the ions, sodium ion and hydroxide, which is one of your polyanions. Now, if you were to carry this reaction out in a glass of water and you were holding it in your hand, you would feel the glass warm up. In fact, the glass would become pretty hot. So what that means in that type of reaction is that energy is being released. And so I'm going to actually add that to our equation here. This is going to be plus energy. All right, and anytime that energy is released, and it's okay to think about this using the same metaphor that I just explained. So you carry out a chemical reaction in a glass of water, which you are holding in your hands, and if you feel that glass of water increasing in temperature, it's becoming hot as you hold it, then you know that energy is being released during that reaction. And in fact, this is what we call an exothermic reaction. So this would be similar, if you want a metaphor, to taking and heating up a piece of zinc and dropping it into a coffee cup full of water. You're going to feel the water warm up. So let's go through the paces on this. All right, and I'm going to take a few liberties here. We're going to do this in a coffee cup, so here's the coffee cup. And in the coffee cup, we're going to have water. And because we've described this before, we're going to kind of go fast with it. So this is water in here, H2O. And we're going to assume that it's at a temperature which is room temperature. I'm going to call this T1, which is 25 degrees C. Room temperature, which would be around 75. And then what we're going to do is we're going to take our NaOH that comes in a bottle and we're going to add it in to our system, or we're going to add it into what we're going to call our surroundings, right? And I'm going to show this way. I'm just going to put a big old fatty circle right here. And on the inside, I'm going to put our reaction. All right, so this is going to be NaOH, and it's going to dissolve, forming sodium ion and hydroxide. All right, now remember, this thing is our system. The reaction is our system because that's what we're interested in. And the surroundings are the water that is in the coffee cup. So I'll go ahead and label that. Now I want you to think about what's going to happen here. Before adding the salt to this, which results in it dissolving, right? Before adding the salt to the water, at a given temperature, the surroundings is going to have a certain amount of kinetic energy. How do we know that? Because the temperature right here is constant. It's not changing. So there's a certain amount of thermal energy that is available within the liquid. Then we add the salt in here and it dissolves. All right? And per the discussion we just had about this, if you were holding this in your hand, you would actually feel it heating up, which means that the temperature is actually going to change. And what you need to understand is that the final temperature this thing takes on is going to be greater than the temperature that we started at. And I need you to think about what that means. It means that the energy of the surroundings has actually gone up, right? So the kinetic energy, or let's put it this way, the potential energy of the reactants, so I'm going to call this R, has been transformed into the potential energy of the reactants. And the potential energy, or excuse me, has been transformed into the potential energy of the products is what I mean. And the products have less potential energy than the potential energy that we started out with in terms of the reactants. And so energy was given off, and that's where this component comes from. And that's why this is an exothermic reaction. So you can think of it this way. Let me change the color of this. So over in the process of the reaction, you're going to have energy which is being transferred from our system into the surroundings. And when this happens, this is what we call an exothermic reaction. So the energy of the surroundings is going to go up. Now, all the same rules apply to this. At the end of this whole process, all right, the energy of the system and the energy of the surroundings are going to be equalized. So in the end, but granted, I know the chemical reaction is maybe a little harder to think about in this way, because the NaOH is going to be completely gone at the end of reaction. All right, there's not going to be any of it left. This reaction goes to 100%. So the only thing you're going to have in solution at that point is going to be the Na plus and the OH minus. But this system is going to be completely equalized in terms of its energy. The final temperature is going to be greater than where we started. And the reason for that is because as the energy comes out of the system into the surroundings, that's going to cause the kinetic energy of the surroundings to go up. And when the kinetic energy of the surroundings goes up, then your temperature is also going to rise. All right, so the temperature is going to rise. Now let's switch gears quickly to another scenario. And that would be where we take ammonium nitrate, which is also an ionic solid. All right, this is a compound you guys have seen before in class. We add it to water and we're going to get ammonium formed, and we're also going to have free nitrate like this. Now, this is the opposite scenario, because if you were holding a glass of water and I dumped ammonium nitrate salt into it, and we agitated it by stirring so that the material dissolves, in a timely manner, what would happen is you would feel the glass get cold, right? It would cool down right in your hands. And in fact, this reaction has that effect to such a degree. You would feel that glass get super cool. It would cool right down in your hands. All right, so this is the opposite type of reaction. And if we were going to write for this one, put the energy in, we would have to put it over here on the reactant side. I'm going to squeeze it in here. So it's going to be energy plus the ammonium nitrate. Let me just put a line straight down through this so we can keep things straight here. All right, so it's going to be energy plus ammonium nitrate. So this is what we're going to call an endothermic reaction. Endothermic reaction. And in these kinds of reactions, if this is puzzling to you, like why is the energy being added in here? You can think of it this way. The ammonium nitrate, in order to get it dissolved, has to be lifted to a new energy, to a higher energy level. It takes an input of energy to cause this material to actually dissolve. Now, if I'm going to sketch this like I did in the other scenario, here's the coffee cup, not the most beautiful thing I've ever seen. Here's our water. All right, so again, this is the H2O, this is the surroundings. All right, and we can insert our system like this. I'll just use a big circle, and we're going to have the ammonium nitrate dissolving into ammonium. Pete's rule, the ions have to be separated, so it's going to look like this. Now in this case, if we draw what's going on with the energy, we're going to have negative E out here. And it's entering the system because this is an endothermic process. It requires energy to drive this process. Let me put that in words. So energy drives this process. All right, and if we knew the temperature in advance, so let's say this is T1, and it's going to be equal to 25 degrees centigrade, same as the other experiment. T2, so again, you're holding this in your hand, and what you're going to feel from a human perspective is the glass is going to cool down. It's actually going to get quite cold. So the relationship between the temperatures is going to be the following, where we're going to have T2 will be less than T1. So the energy of the entire system, the potential energy of the system and the surroundings is actually going to go down, because once the ions are dissolved, the system plus the surroundings is going to be now at a newer, lower temperature. And what does that mean? It means that it lost kinetic energy overall. Well, where did that energy go? It was required to force that solid to separate into ions and then interact with water molecules. Whereas over here in this scenario, all right, the NaOH dissolving in water is exothermic, and in this case, energy is actually released because the bonds that form between the ions and the water are actually lower in energy than the bonds that form between the ammonium and the nitrate. All right, so this concludes this particular video, and the next one in lesson 5, what we're going to do is look at this example in more detail. Remember what I've said. If you're having a hard time understanding, then you need to pause the video and think about it, or go back to the beginning and listen to it over again.